of a quotient, right? Meg is saying, thank God, no, I don't have to know these things. Well, it's just the derivative of the top times the bottom minus the derivative of the bottom times the top, all divided by the bottom squared, right? Right. Okay, that's what this is right here, okay? Vx, that's the change, that's the velocity in x times z, minus the top x times the velocity in z divided by z squared, multiplied by f, that's just a constant. Same thing down below, okay? Then we start to expand this stuff, and we get this nice little formula here, okay? So when you look at it, that's still kind of ugly because you don't actually know what Vx, Vz, and Vy, you know that they're from back here. Well, it turns out you can write them pretty beautifully, for some twisted definition of beauty, in this very simple formula here, 1 over z at some point xy times a times t plus bxy of omega. And let me show you exactly what that is, okay? So here I've rewritten it. So this is the motion. So u is how much it's moving at some point xy. So we know the point xy in the image. The question is, how much motion are we seeing? So we've got the u and the v. That's the motion in x and the motion in y. All right? And what it does is this formula relates the translation and rotational component of the point out there in the world. These are world t and world omega, to how it's moving in the image, okay? Thing to realize is that this quantity A is just a function of things we know. We're assuming we know the focal length of the lens, and if we're at some point xy, we know what that point x, this is little x, little y. This is the location in the image. Cap x, cap y, cap z, out in the world, little x, little y in the image, all right? So you'll notice that A is just this function. B is a little more complicated, but it is still just a set of things we know. Okay? So if you tell me some point and you tell me the focal length, I can tell you this A matrix and this B matrix. I might not know t and omega. I might be wanting to solve for t and omega. Okay? But A and B I know everything of. So there's only one really important and interesting thing about this equation. And here it is. Notice the z value of the point. So this is written in a funny way, right? This is z of xy. What does that mean? That means if I'm at some point xy, remember that's a ray in space, right? Z, in the coordinate system of my camera, is the depth of that point. You'll notice that this thing is made up of two terms, the A term and the B term. The A term has the translation in it, the B term has the rotation in it. The depth is only in the A term, the translation term. Why? Think about motion that happens. If you remember, a projective camera just has rays out in space. And you can think of the rays as going out till they hit something, and they stop. Okay? Now, if I rotate those rays, in fact, maybe I can draw this. So here's my point, and here's a whole bunch of rays. Let's suppose here's my image plane for frame 1. Okay? If I rotate some angle, so my image plane will now be there. So before, this ray was hitting at that point on the plane, and now it's hitting at this point on the plane. So if before it was in the middle, now it's to the right-hand side. Okay, fine. Notice I didn't tell you how far out the rays went, because as the image plane rotates and it cuts through the rays, it doesn't matter how far the rays go. So the depth has no impact on the amount of motion that you see as you rotate. But if I translate, the depth matters a lot. Remember the whole thing about the moon, right? That the moon seems to follow you? And we're going to demonstrate this right now. So now, get out your rulers on the screen, right? I'm going to take a step to the right like that. Okay? So the amount of motion that you saw is whatever it is. All right? Now, I take the same size step. Megan, did I move in more of the field? Did I move much further across the field than I did when I was in the back? Megan's going, yes. In other words, the amount of motion you get, this is called motion parallax, is a function of the depth. So that really dorky demonstration is why the z value is only in the term that has the translation component. If you don't translate, the depth doesn't matter in terms of how much things move. That's why we talked about when you build panoramas from rotation, I can just map the planes. I can map the rays because it didn't matter what the depth was. This is the general motion model. I hope this was not too pedantic. I like tying back the stuff we're doing now with the stuff we did before. Suppose I know something about the motion, the geometry of the points. For example, let's suppose that I'm on some plane. All my points are on a plane. Here's my equation of a plane. So all my points, x, y, and z, satisfy this. Remember, we showed this before. When we were mapping everything on a plane and saying how it would have moved, we ended up with a 3 by 3 matrix, but it was a homogeneous system, so we could scale it any way we wanted. So if we wanted to, we could set one of those elements to a 1, and then we only had to solve for the other 8. There were 8 unknowns, so therefore we needed how many points, Megan? How many points? How many points? 4 points. Here is the equation using just the xy values, and you'll see a 1, 2, 3, 4, 5, 6, 7, 8, 8 unknowns, 4 points needed. So when it's on a plane. Now, if the plane is very, very far away, what does that mean? Well, what it means is if the difference in the distance on the plane is small compared to the distance from the plane to the camera, you can show that this is the simplified model, right? It's just 6 unknowns, otherwise known as an affine transform. This is one of the reasons that affine transforms are used so much. When things are on a plane, on a wall, on the floor, even on maybe front of a body for a while, mine used to be more planar than it is now, for small amounts of motion, you can think of this being as a plane that's relatively far away. And what that means is that that plane will undergo an affine transformation. So, if we have these motion models, we'd like to be able to use them within all of that motion math we did before on the brightness constraint equation and the optical flow and that kind of stuff. And we can do that directly. All right. So here we have our image showing you the math of an affine transformation. Now, you all remember your brightness constancy constraint equation? Yes, 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 yes. Looks like that. Remember, what this says was that the dot product between the u and v, that's the amount of motion, and the gradient, has to essentially remain constant with respect to the change in intensity. So that was the brightness constraint equation, right? We had 2 unknowns, 1 equation. So the way we fixed that before is we assumed that all the points had the same uv. Suppose instead of saying it's the same uv, we assume that it's the same affine model. That means that we substitute in for u and v the equations from above. Didn't that work out nicely? All right. So instead of just saying u, we're going to say, okay, over this window, we have to find the A1, A2, A3, A4, A5, A6. So how many unknowns is that? 1, 2, 3, 4, 5, 6. We have 6 unknowns over the window. So how many points are we? How many equations do we need? Well, we need at least 6. But now our assumption has been relaxed. Before, we required that everything be moving constantly, so you can't really let your windows get too big if you're going to require that they be constant motion, because as you let your windows get bigger, they may not be moving constantly. But if you can allow for an affine deformation, so they're not all moving the same, they're all just the same flow, like maybe they're rotating around, now I can have bigger windows. So what we do is we take this equation, all right, each pixel provides one linear equation with 6 unknowns, so we're going to do that same least squares minimization we did for Lucas-Canati, but now, instead of having a constant UV, those 2 unknowns over window, we're going to use this linear model with 6 unknowns. And we do exactly the same thing we did before. It's going to be a minimized squared error, least squares, and that allows you to solve for that over that region. And because the pixels are moving differently depending upon the xy, I can have a whole area that's rotating. It's one model. So all of those pixels use the same A1, 2, 3, 4, 5, 6 because it's the same rotation. Right? It's not the same little vector, it's the same model. So it can be a much more robust way of doing things. So here is a version of the Lucas-Canati now, and it's taken from the original paper. It's a paper that's cited a lot and almost impossible to find by Jim Bergen and Anandan and Keith Hanna way back 1992. And the thing that's different about this from Lucas-Canati is instead of computing m for motion, which was just the specific motion everywhere, we're doing these little m, which are the model parameters. right? And so you have to compute the model parameters. What if over here I've got something spinning, and over here I've got something translating? No, sorry, expanding. I'm expanding. What I've got is I've got different motion regions, and I need to find those different motion regions. So there was some nice work done, again, a long time ago by Ted and John Wang on what are called layered representations. The idea is, what if we could break the image up into a bunch of different motion regions? Okay, and in fact that's illustrated here. So this is a figure taken directly from their paper. So the idea is we have a hand that's moving across, and it's against the background of checkers, squares moving this way, because we're always waving our hands over moving checkerboards. I don't know, it's just what they did. Okay, so here they're showing you each of the frames, and clearly what you'd like to do is you'd like to be able to recover those different elements, that the front part is moving this way and the back part is moving that way. So here's how we do it. Here's our affine equations again. So we have these local flow estimates, right? So compute some local flow some way. Maybe use straight Lucas-Canati, all right? Notice that this one equation, let's just worry about the u for right now. That's a linear equation in x and y. That's just sort of a plane. In fact, if we were just doing this in 1D, it would be a line, right? Forget the y, right? We'd just say that u is equal to a1 plus a2x. It would just be a line. These are linear systems, all right? So the way this works is the following. And here's an example done from 1D, again taken from their paper. Suppose this is the velocity as a function of x. So we're only showing you the 1D version because it's a lot easier. And let's suppose that this is the true flow. And what we mean by the true flow here is that the foreground region is actually moving in some way, and it's not a constant because it's an affine flow, that is, it's planar, and the background might be moving some other way. And what we want to do is we want to be able to find that. So the first thing you do is you do a local flow estimate. Lucas-Canati everywhere, let's say. That gives you some vectors. Now, those vectors are not perfect. They are what they are, okay? Well, what you do then is you take a look at those values. Where do I see big jumps? So I see a jump there, I see a jump here, I see a jump here, I see a jump there. And I break that up into those segments. And then what I do is I take a look at the segments and I say, which segments seem to be along the same plane? And it's planar because of this affine equation. And when you do that, you get to automatically separate out the foreground motion from the background motion just by fitting, it says line fitting, but essentially by fitting the affine plane to what's going there. To actually make this thing work requires a lot of detail. Finding those breaks is not trivial. Clustering things is not trivial. Fitting the lines, well, that's pretty trivial once you found the clusters, but you got to find the right clusters that belong to the right lines. There's a lot of detail, and you can take a look at the paper that we mentioned. I just want to show you the results here. So here is again the flower bed sequence from MPEG, and here what you can see is they've put down what the different motion fields they captured were. One was the flower bed. And you can see that flower bed is kind of like a plane that's moving in a particular way. So that's one motion. The house with the trees that are sort of right by the house is another motion. And the tree in the foreground is another motion yet. So it has done a motion segmentation of the sequence. So at the end of the day, it doesn't tell you that all the points are moving arbitrarily, like Lucas-Canati does, or even smooth Lucas-Canati. It doesn't tell you that they're all moving the same way. What it does is it gives you this broken up pattern, or this broken up image sequence of saying this region is moving this way, this region's moving another way, and then this background region that's occluded by these regions is moving yet a third way. And this is motion segmentation. There's a lot of work lately on video segmentation. It's an active area of research, and there's always this question of you want to break it up into enough pieces that you get out the different elements, but not so many pieces that you take something that really should have been kept together and you break it into two parts. Like I said, that's the end of the work we're going to do on sort of direct motion. So basically, we've looked at two generally different ways of doing this, of doing motion estimation between two frames. One that can handle sort of large range sparse. We find particular features and we come up with descriptors, then we find them in the second image. We think we know which matches are right. We guess to see which pairings are correct, look for a motion model, and maps them across. And that works well. We can have lots of differences between the points, but we have to have a consistent model across them. And then we do that random.